Hello, in this video I'm going to solve the following problem for you. State that whether the following integral converges or diverges and justify your claim. Integral from 0 to infinity, absolute value of sine x over x squared dx. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. The answer to the problem is the integral diverges to infinity. Okay, now let us try to understand the problem. So this is an improper integral, obviously, because you see this infinity up there. So it shows that this is an improper integral of the first kind. But because 0 is also problematic, that is also an integral of the second kind. Why? Because if I take the limit of the integrand over x squared, x goes to 0 from the right side. Okay, so this means that I don't need the absolute value because x is in the first quadrant and sine is positive there. So this becomes the limit. I remove the absolute value sine, and then instead of x squared, I write 1x here, and then I write 1 over x there. X goes to 0 from the right-hand side. So the limit of this part is 1, and the limit of that part is plus infinity, so this becomes plus infinity. So this is really making problem, yes? So it is improper integral, both kinds in one problem, so we have to break it up. So, and the good breaking point is integral from 0 to pi over 2, absolute value of sine x over x squared dx. And then the next one I will consider from pi over 2 to infinity, an absolute value sine x over x squared dx. So I will consider these two integrals. If both of them converge to some limits, then of course I can conclude that this integral converges to the sum of the values of these integrals. But if at least one of them diverges, then the whole integral will diverge. So I will focus on this part, and let me call it I. Okay, but be careful, still we are in the first quadrant. Yes, in the first quadrant between 0 and pi over 2, sine is positive, so I can just simply write it as 0 to pi over 2 sine x over x squared dx. Okay, but this is only improper integral of the second kind, yes? Okay, so I need some inequalities. The inequalities that I need are these. So I want to prove that if theta is an angle from 0 to pi over 2, I want to prove that sine theta is greater than or equal to 2 over pi theta. This is what I want to show. Okay? In order to do that, I need also to prove that if theta is somewhere between 0 and pi over 2, then tangent theta is greater than or equal to theta. Okay, so here I can also include 0. So the first thing that I will do, I will show this inequality. Using this inequality, I will show this inequality, and using that inequality, I will be able to compare this integral with a famous integral that I know it diverges to infinity, and then we are done. Okay, so let us concentrate here. Theta is somewhere between 0 and pi over 2. Of course, if theta is 0, this inequality is trivial because the left-hand side becomes 0, the right-hand side also becomes 0. Okay, so let us concentrate on this interval from 0 to pi over 2, and let me define a function f with this domain and this. This is the standard trick, yes? If you want to prove these inequalities in which an angle, sine, cosine, tangent of the angle and the angle are involved, the standard method is to define a function as the difference between them and try to use a derivative to prove that inequality as I'm explaining now. Okay, so I move this to the left, tangent theta minus theta. I define f to be a function with this domain and this rule, so I differentiate it with respect to theta. The derivative of tangent theta is simply secant theta squared, and this is just minus 1. But secant theta squared is 1 plus tan theta squared minus 1. 1 and 1 are cancelled, so it becomes tangent theta squared, and it is always positive there. It's strictly positive. So this means that the function f is an increasing function on this interval because its derivative there is positive. Okay, so if that is the case, because theta is greater than 0 and f is increasing, what can I conclude? I can conclude f of theta is greater than f of 0. This is the definition of a function which is strictly increasing or increasing, okay? So f of theta is nothing except this expression is greater than f of 0. I have to replace theta with 0. But this is nothing except 0. I move theta to the other side, then I have my inequality. Okay, so tangent theta is greater than theta. And of course, if I also include 0, because tangent 0 is equal to 0, equality also holds. So in general, this is a true inequality. Okay. Here, now I want to prove this one. First of all, you see that if theta is 0, the left-hand side is 0, the right-hand side is 0, they are equal. If theta is pi over 2, sine pi over 2 is 1. If I put pi over 2 here, and then this becomes 1, 1 is equal to 1. So it means that for the extreme cases, this equality holds, and automatically the inequality also holds. So let us concentrate on this interval for proving this inequality. The first thing comes to mind is using the same trick. So let me define a function g on this domain with this definition. Sine theta minus 2 over pi theta. I want to use the same trick. But then you will see it will not work. So because if I take the derivative of this becomes cosine theta. The derivative of that one is just simply 2 over pi. But 2 over pi is a number less than 1. So it is not guaranteed that cosine theta minus 2 over pi is strictly positive or negative. It might be somewhere, sometimes positive, sometimes negative. So that's why apparently that idea does not work in this case. So how should I escape from this situation? You have to be a little bit creative. So I will take the same interval, but I define the function with this domain in this way. Sine theta over theta, and then minus 2 over pi theta. 2 over pi. So let me see. Yes, let us define it like this. Yeah, this way. So what I'm doing an alternative. So instead of proving this, I am comparing sine theta over theta with the number 2 over pi. Okay? Because if I know which one is bigger than the other one, I can go back and conclude something about sine theta and theta themselves. Yes? So this is the trick. Now I differentiate the derivative of g. This is the quotient rule. The derivative of the numerator, cosine theta, multiplied by the denominator itself, minus the numerator multiplied by the derivative of the denominator, which becomes sine theta, divided by the denominator squared, and this is just simply a constant, so it becomes 0. Okay, now what I will do, I will factor a cosine theta out in the numerator. So this becomes cosine theta, and then I will have theta left from here, minus sine over cosine, which becomes tangent theta. and then divided by theta squared. And the derivative of this one is, of course, 0, yes? Now, because I am working in this interval, cosine in the first quadrant is positive, theta squared is positive, and we just learned that tangent theta is greater than theta if I am working in that interval. Yes. So this means that this is negative. Negative, positive, positive, so it becomes negative. What does it mean? It means the function I defined in this way on this interval, its derivative is negative, so it means it is decreasing. So it means that g is decreasing. And what do I have? Theta is less than pi over 2, and because g is decreasing, what can I conclude? I can conclude that g theta is greater than g of pi over 2. Okay? And then what is g theta? G theta is this expression, which is sine theta over theta minus 2 over pi is greater than g of pi over 2. So it becomes sine pi over 2 divided by pi over 2 minus 2 over pi. Okay? So this means that sine theta over theta minus 2 over pi. But what is this expression? Sine pi over 2 is just 1. 1 over pi over 2 becomes 2 over pi. 2 over pi minus 2 over pi is 0. So this becomes greater than 0. And then what I do, I move it to the other side. So it becomes sine theta over theta greater than 2 over pi. But because theta is positive, I can multiply both sides of this inequality by theta without having to be worried about the direction of the inequality. So it becomes sine theta is greater than 2 over pi theta. This is valid if theta is strictly between 0 and pi over 2. As I mentioned before, if theta is 0, this equality holds. If theta is pi over 2, the equality holds. So in general, this is completely correct. Okay, so now I want to use this inequality for this inequality. So here, because x is between 0 and pi over 2, okay, this is the interval of my integration. So then what can I do? I can say that, so I can also keep equality, it doesn't matter. So sine x is greater than or equal to 2 pi over x, and then I divide both sides by x squared greater than or equal to 2 over pi times x. So I was able to show that, of course, when I divide by 0, I have to take this 0 out, yes? And when I divide by x, I have to make sure that this is not 0. So this is valid on that interval. Okay, and now I consider this integral. An integral from 0 to pi over 2 of this function. So 2 over pi x dx. Of course, hopefully you remember that this integral diverges to infinity, but if you have forgotten, you can use the definition. This is, of course, an improper integral again of the second kind, because at 0 I have problems. This function becomes unbounded close to 0 from the right. So I would write it as limit of epsilon, for example, going to 0 from the right, of integral from epsilon to pi over 2. And then because 2 over pi is let me write it here, 2 over pi x dx. But that is a very simple integral to do. So this becomes the limit. Epsilon goes to 0 from the right-hand side. This becomes 2 over pi ln of absolute value of x, where x goes from epsilon to pi over 2. And then I replace it. So this becomes the limit of 2 over pi ln of absolute value of pi over 2 minus ln of absolute value of epsilon but then epsilon goes to 0 from the right-hand side. ln of pi over 2 is just a number, but ln of epsilon, when epsilon goes to 0 from the right-hand side, becomes minus infinity. Minus minus plus infinity plus a constant multiplied by a constant multiplied by a positive constant becomes positive infinity. Of course, if you remember that this integral diverges, you were done there. But if you have forgotten, you can do it. Now, this function is greater than or equal to that function. Both of them are positive. They don't change the sign in the middle of the interval. And then the right-hand side integral diverges to infinity. So I can conclude the left-hand side integral also diverges to infinity. Okay. So if I go back, I realize that this diverges to infinity, to positive infinity. But that one is also positive because the integrand is positive. So this diverges to infinity. I really don't need to do anything here, but I know that this is also positive. Okay, so the whole integral diverges to infinity. Yes, so that's the solution of the problem. Of course, if you remember all these formulas, you don't need to prove them, but I want to make a complete presentation of what we really needed. These are very famous inequalities. It might be helpful if you remember them for the future. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.